now let's start. Before that, let me see who you are now. So the first one, 附录军
附录语音。
附录语 ，sorry。李成浩啊，赵佳琪，崔家园，陆一凡，姚如歌，李宗浩，Raise key， OK， John Knott， OK， and another one is Dean, not here. Tina, 蔡家峰。Okay, if we have 14, we have 14 students in this course, and have 4 foreigners and 10 Chinese. Okay. So this course, its name is Radar Remote Sensing and Channel Modeling, and it should be produced by our English. And so let me introduce myself. I'm Jianjun Ma, and from Institute of Microwave and Telephone Technology. I think most of you also from this institute also. So for this course, we have 12 lectures, and for each time we're gonna spend almost 2 hours. And this course, it starts from, it's usually Monday and Wednesday, so from the 9:55 to 11:30. And so I would also wanted to tell you the final score, the accounting for the final score. So the first one is we have class attendance and participation. And participation, so it can account for 30%. The second one is the a report. This report is really as our homework. And it should be based on one publication. So at the end of this course, I would give you multiple publications, and hope each of you could choose one and then do a report based on that. So it can account for 30% or so. And the last report is the final exam, right? So the final exam is representation. As final exam. So this presentation is still based on your report. So you finish your report, then present it. And each one maybe spend on 15 to 20 minutes, just like a conference presentation or oral presentation. So this can account for 40%. So let's back to this course. So it is called the radar remote sensing and the channel modeling. So you can see it has 2 parts, right? The first part is radar remote sensing, and we're gonna introduce the mechanisms for the radar detection. And for the channel modeling, it's gonna be based on it's gonna be concentrated on the theoretical models and calculations for a radar signal or for the communication channel, something like that. So usually, if we want to, because why we are concentrated on the radar remote sensing, is because, as we all know, the microwave, all right, is really for our institute, is for a microwave, millimeter wave, and terahertz waves. So the radar remote sensing for this course, we are also more concentrated on the microwaves and sometimes the terahertz waves also. So if we wanted to, I think most of you maybe your research focus are on the radar, right? Some of you may be on the radar detection or the signal processing or the system design, something. So if we wanted to do such things, one of the basic problem we need to know is about the detection mechanisms for that. So to understand how the active or passive the microwave radars or microwave sensors, usually because we have the passive radar and the passive radar and the radar used to detect the radiations from the objects itself. So we would also more concentrate on the sensors. So if we want to understand how the active or passive radars or sensors to detect the object, we need to know the interaction of the electromagnetic waves, all right, with the material. So for this one, for this course, firstly, we needed to get a short review for the electromagnetic waves and the propagation of the waves also. So, but here the material we would want it to be more concentrated on the, for example, the Earth's surface, or the atmosphere. So for atmosphere, as you all know, we now we have some projects from in the Foreign Institute for the meteorological problems. All right. So here I would want to introduce the interactions with the atmosphere also. The atmospheric particles like the rain, the snow, the fog, or the wind, something like that. So, if we wanted to know how the electromagnetic wave to interact with materials, usually we have several mechanisms, right? Mechanisms, simple mechanisms. Do you know? If the electromagnetic waves, if it interact with materials, several basic mechanisms. Any kind? For example, absorption, right? And also the scattering. And also transmission. Right? And sometimes maybe reflection. But sometimes we really immerse the reflection into the scattering, right? So this interaction usually involves one of them, or sometimes a combination of several of them, or all of them together, and this can give us some topics to interact or investigate the interaction problems. So for the material, we have to know, also we have several kinds, we have many kinds of actually, right? We have many kinds of materials. But here we're gonna classify it into mostly two types. The first type is lossless material. Then another one should be lossy, alright? So for the lossless material, that means the material when the electromagnetic waves propagate or transmitted through this material, it would not suffer any absorption from it, right? So actually, sometimes if we set, for example, if we use the lenses, sometimes if you do some researches on the optics or on the terahertz waves, we're going to use the lenses. We're going to use the lenses to make the to get a higher gain, or to make the beam size smaller and more directional. So the lenses usually use Teflon or use DPT, something like that, when because such materials is usually considered as lossless material. So we just wanted to use them to focus the beam path, the beams, and do not want it to exert any absorption losses on these electromagnetic waves. But mostly, or most of the materials, or most of the natural materials, it should be lossy material, alright? So usually we use it to express such kind of material. We can express it as for the material, the most important parameter to represent it is what? The most formula or popular or mostly used parameter for it, dielectric constant, right? Dielectric constant. And we already use epsilon to represent it, right? So it is usually expressed as a real part and an imaginary part, right? So this is a real part, this is imaginary part. So for the lossy media, it's really determined by this imaginary part, right? So when this part is large enough, it's gonna make the this material is a lossy material, and when the electromagnetic wave propagates through such material, it's gonna suffer a significant or a large absorption. You ready? So why this imaginary part is gonna be accounts for the absorption? That's because it is related to the conductivity of the material, right? So that's would be introduced later. But here, when we wanted to interact or investigate the interaction between the waves and the material, we need to know the parameters of this material also, but most importantly, we also need to know the parameters for the electromagnetic waves, alright? So for the electromagnetic wave, or if you want to simplify it, you can call it EM waves, there should be also several parameters, right? The first one is its frequency, or its or wavelength, alright? And the second one is the what? Most importantly, for the EM waves, yes, its phase. And its phase is also related to sometimes its polarization, alright? So this is for the waves. If for the devices, maybe there should be more parameters such as the radiation pattern or the modulation scale, or the the channel numbers, or the channel numbers, something like that one. So all these things should be considered if you want to analyze or investigate the mechanisms between of the interaction between the EM wave and the material. So for our investigations, when we back to the propagation of the electromagnetic waves, the first thing is when a time-varying electric field then induces the magnetic field, right? And inversely, the time-varying magnetic field would also induces the electric field. And when we go back to the interaction of the material, so if the material is such as it is kind of a homogeneous medium, so we usually consider materials homogeneous. Why? That's because the EM waves will not suffer or can just maybe degrade the scattering performance of such kind of medium. And if there is the material or the medium is homogeneous and there is no other objects such like obstacles, the obstacles or the material interfaces then we can define the EM wave is unbounded. So, if this is the simplest situation, alright? Actually, if we wanted to conduct a theoretical model for the channels, we need to consider many kinds of objects in this scene or in the environment. For example, for the Wi-Fi signal, right? If we wanted to conduct its channel modeling, for example, the transmission through walls, velocities, outdoors, and the reflection by them also, and there are many chairs, tables, laptops, cell phones, alright, should be considered in modeling. But here, if we just consider the medium, and it is homogeneous medium, then this thing should be neglected. So when an electromagnetic wave propagates through the lossless medium, there is no absorption, right? But when it propagates through the lossy medium, so the channel power gonna be degraded or attenuated, right? And then it is really converted to what? The lost power. Converted it to heat, alright? follows the energy conservation. Alright? So the lost power is converted into heat. So that's why there are some researches on the biothermal heating effect by the EM waves. So when the large power of the EM waves is focused onto the biology or humans, it's going to generate the heating effect on the skin or something like that. It's because it's lost the power. It is converted to heat. So, if we want to see how the EM wave propagates, the first thing we need to know is how the source is, right? So, if the source is really the shape of the source is going to determine the wavefront of the EM waves, right? So popularly we have two kinds of that. The first one is, anybody know? If we wanted to consider the wavefront, the EM waves can be classified into several kinds, right? Spherical and plane, right? Mostly these two kinds. So for spherical waves, that's because its wavefront is like a sphere, alright? For a dot source sometimes, and the omnidirectional antenna sometimes. So the waves is really a spherical wave because it's wavefront, right? So sometimes or many times we would also want to employ the plane waves, right? So when a dot source generate the its wavefront is like circle, like this, alright? So if our antenna detector is not long, its aperture maybe it's small sometimes, and when it compared to the radius of the wavefront, so we can consider this part, this small part, is plane. It's just a plane on a spherical sphere, not a sphere. So some kind of wave, we can call it a plane wave. And another thing we can achieve a plane wave from spherical wave is we add a lens, alright? So we add a lens here. So after that, its wavefront going to become V set suitable focal length of the lens when it is compared with the radius of the spheres at the side, so we can get a plane wave, a uniform plane wave like this. So I think for the maybe this is not very often used because in the microwave or the military range for terahertz and optics, it is really used because we wanted to collimate the beam. Collimating beam, right? So we want to make it collimated, we need to use. Sometimes we already use maybe 2 or 3 lenses to achieve that. Make the beam is make it to be a plane wave. Also, the beam width is reduced, and then we would have more power or energy concentrated, and exert to achieve a much longer propagation distance. So for the material, we have several parameters, right? And it's called constitutive parameters. Previously we said we have the dielectric constant, right? And it has several other parameters. Constitutive parameter. So the first one is the dielectric constant epsilon. It has another name, all right? Another name is permittivity, all right? Permittivity. And for permittivity, it also has permeability, right? And also, we have another one to classify whether it is conductivity. And also, we have another one as the volume charge density. So for permeability or dielectric constant, we call it a dielectric constant. Actually, it should be all of them, but mostly we are concentrating on this one. So its unit is farad per meter, right? This one is Henry per meter. This one is Siemens per meter. Siemens per meter. This is capacity per meter. This one. Chart. So for the permittivity, it can be expressed as epsilon node times epsilon r. Alright? Epsilon node is the permittivity of free space or vacuum, and it should be a constant. And this one is the relative permittivity. Alright? So the relative permittivity is mostly determines the mostly used to classify for the material classification, because at one frequency, different materials could have different the permittivity, right? And so the variation of epsilon r is really used for the object rectification, because it is material dependent. So in this course, we would express it as epsilon prime. Why we wanted to express it as epsilon prime is because we wanted to use it to express the total or the complex permittivity or the dielectric constant epsilon. All right, as we mentioned earlier, it should have two components. The first one is the real part, and then an imaginary part. So for free space, so this one can be expressed as epsilon node, epsilon prime. Here, we just consider it as a lossless medium, all right? So this one has the imaginary part. For a free space, first one. For free free space, the free space its relative dielectric constant should be 1. Alright? Should be 1. So for free space, you're right. So when we wanted to analyze the propagation of the radar signal or the channel, when it propagates the raw free space to the object between both sides, the medium when it propagates its dielectric constant, or its relative dielectric constant should be 1 actually, and the permeability, I think most of you should know, right? It's U node, and it's really its value in the free space also. And for the free space, its conductivity should be node, right? And its charge density should also be node. But actually, if this is an ideal free space, actually there should be maybe some charges. For example, for the Earth sphere, the ground is around 5 to 10 kilometers above the ground. There is Earth sphere layer, and it has charges inside, even though its density or its density is not very large. But here, we just consider an ideal situation here. So, second is for the dielectric material, which are mostly used, alright? For example, the wall, the glasses, the table, something like that one. So this can be considered as pure dielectric. So for the pure dielectric, the epsilon prime, it has its own values, right? So if you read some applications, they did some measurements on such parameters, I find it's usually maybe several. Its unit, it has no unit, right? Because it's relative materiality, so it has no unit. It's really around maybe several numbers, or 10, or more than 10, or tens of that. But it cannot be very large. And the permeability mu can still be mu node. Can still be mu node because mostly our natural material cannot be ferromagnetic, right? Not ferromagnetic. And for the dielectric material, we usually consider as charge density is node, and conductivity is node also, so 0. So this is for the pure dielectric materials. So that's why for dielectric materials, we consider it as no imaginary part because its conductivity is 0. But actually, it is not, right? Because we do. It is difficult, very difficult to get a pure dielectric material, right? So, for example, for the chip fabrication, we need to get very pure silicon wafer. So we know that this fabrication is very difficult. The third one is the conducting medium. Conducting medium. So for conducting medium, we know that its conductivity cannot be 0, right? First thing. The second thing is charge density. Maybe it is charged or it is not charged. So This one, it depends on the situation. And we really consider its permeability. You know it also, except for the ferromagnetic materials. And its permittivity or relative permittivity, it is also has its own values. And for the metal, for example, for the gold, this value can be very large. It's around thousands, sometimes tens of thousands. Like that value is very large. So that's why we already set the gold surface as a perfect reflector for the terrestrial waves, because this part is very, very large, a large value. So the for conducting medium, it can absorb the energy by the electromagnetic waves, right? Because its conductivity is not zero, and later we would want to conduct the expressions for the real part and the imaginary part based on the other parameters of the material and the parameters of the EM waves. So now first, we're going to go back to the Maxwell's equations, right? I think most of you should be very familiar with that when you are preparing your entrance examination as a master student. So it has 4 equations, right? So the first one is, of course, rho over epsilon naught, epsilon prime. It is the Gauss law. And the second one is the Faraday's law. It's a curve of the electric field. Can be minus partial h, partial t. So it's the Faraday's law. And third one is gradient because there's no magnetic pole, right? So this is the Gauss's law also, again, for the magnetism. And the fourth one is Ampere's law, the curve of the force, current density plus 1 epsilon naught, partial E, partial T, Ampere's law. So we have 4 equations for that one, and I think most of you should know that. How it can be conducted to get expressions for the magnetic waves. So the first thing we need to know is, if we assume the time variation is a sinusoidal function with respect to the angular frequency. The angular frequency, we already use omega, alright, to express that. And it varies, the electric field varies with time t. Only on a sinusoidal equation like this one, alright? Usually, if we wanted to express the space sometimes, or the vector phasor, if we express the electric field with respect to the vector phasor, it can be expressed as the electric field. It varies with the space, right? X, Y, zeta, and also time t. And it can be represented as, because for the electric field, it should be a real number, right? So the real part of it. But actually, we already use that to express it as x, y, z, the vector phasor, and also its phase part. The phase part we already use an exponential function to conduct that. Like this one. So it makes it to be more clear for that one. And this one is vector phasor. So the vector phasor usually because from here, because the electric field varies with respect to time, so it can be used to represent an instantaneous electric field, right? So for each time, each position, we get the values of it, and we can analyze the field variation with respect to time. So for the magnetic field, we have the same representations, right? Just represent E with H. And when we substitute these equations to Maxwell's equation, we can get the because here it varies with respect to here, right? So we have several functions. So we can get the this part gradient as it keeps this one. So this one get the curl of electric field as the minus omega and minus j, I guess it's minus j h, alright? And this gradient 0 and this curl plus j plus j omega prime is known electric field, right? So we get the expressions for this. So now here, what we consider is when we back to the former slide, we consider the permittivity. It only has a real part because we consider it has no absorption. It is a lossless medium. But if when we wanted to introduce the lossy medium, so here this term, it is called, it has name, right? It is conduction current density, alright? Conduction current density. So that means for conduction current density can be expressed as its conductivity times electric field, right? So that means for a magnetic field can be expressed as this part plus this part, right? So when we combine them together, this one. So from here, if we wanted to compare it with the okay, let's take a short break. I'm gonna come back 10 minutes later, 5 or 10. OK， 那我们休息一下。那个。Okay, let's come back. And so from here, if we want to convert this term as B like this, so you just want to express it as J omega epsilon times E, like this one. Make it to be symmetry with this equation already slow. So here that means this term becomes omega, right? So this one becomes minus plus epsilon okay, like this one. So the relative part can be this one. So this part is defined as epsilon. So it can be epsilon equals epsilon prime times a plus sigma over j omega no equals y price minus j, right? This one. Like this one. So this is the real part, and this is the imaginary part, right? So the dielectric constant, or the complex dielectric constant, can be expressed like this. Dielectric constant. So if sometimes if you want to calculate the interaction of the channel modeling or channel modeling, if you just find, sometimes you can only find the refractive index of a kind of material, right? So when you use that for calculation, you're going to find that there is a lot of difference, or there's a lot of discrepancy to both your calculation and the merit data, because you lost the information about the imaginary part. So if we put this part into the theoretical model, we can get the propagation constant of the electric or magnetic field. So first thing is we want to get the propagation of the electromagnetic field. We take another curve of this equation, right, on both sides, and get like this one, right? So it equals the minus j omega mu, the curve of H, right? So then a lot of calculations, and we get the times that plus omega square mu node equals 0, right? So this is the wave equation, or the homogeneous wave equation. Wave equation here. So for this wave equation, it can be expressed as, if we want to define for a format of a wave equation, it can be defined by minus, right? Minus gamma square. This is a standard wave equation, right? it can be defined the propagation of the wave. So that means we get mu square of the it equals minus omega square mu epsilon naught. So this equation, this parameter of the parameter gamma is called propagation constant. So remember this expression because it's going to be used for our later calculations. So for the electric field, it's the same thing, all right? So now, when we want to go back to the plane wave propagation, so for plane wave propagation, we usually has a parameter to define its propagation, or sometimes it can also indicates the propagation direction, right? For the plane wave. Could you remember? For plane wave, its propagation, the most important parameter is k, right? A wave number is a vector, so it defines its propagation direction, all right? So for a plane wave, its wave number scalar part. Okay, sometimes you really define it along the wave direction, right? So it can be expressed as omega square root mu epsilon prime epsilon naught, right? So it's 2 pi or half and time divided by s propagation speed inside of the material, all right? So if we go back to this equation, in the lossless medium, the gamma square equals minus omega square mu. Imaginary part can be neglected, right? It becomes like this one. So that means it can be expressed as minus k square, all right? So for the lossless medium, the propagation constant equals minus the square propagation constant minus the number here. So for the lossless medium, its wave equation can be expressed as loss k square, all right, equals 0. So that means sometimes when we want to see the propagation of the plane wave, it really can see this equation, right? And minus means it propagates along the theta axis, all right? It's along the theta axis, and when it is positive, that means it propagates oppositely to the theta axis, all right? It's not this direction. So that's why here, of course, it is inversely to the square of the propagation constant. So if we consider here, we define our electric field. It has the x component, y component, and z component. Here, if we wanted to define it only along the it has only an theta or the x component. For example, if the electric field, but here, of course, it can be 1 to 2 partial square partial x, partial square partial y, and partial square partial theta, plus k square, right? Equals 0 here. And if we wanted to simplify it, or we assume a uniform plane wave, and it has the its electric field along x, y plane, for example. And if we assume this one, that means it only propagates along the theta direction, right? Because its electric field is along the xy plane, or is inside of the xy plane. So that means these two sides is raised, and this is 2 times derivative. So d squared d theta e. We just consider the x component firstly, plus k squared ex equals 0. So from this equation, you can see if we wanted to get a solution for this equation, the solution of this equation, it has 2 parts, right? The first part is one along this part, right? And the positive side. So 2 parts, right? Because to orders and derivation, they're gonna lead to a minus k squared, and then they're gonna satisfy this equation. So this one. So here, as we mentioned here, so the negative means it along the theta direction, and the positive means it is opposite to the direction. So both sides together and get the solution of this one, right? So as we conducted for the such a kind of equation, it has 2 parameters, a and b, right? So this parameter should be determined by the electric field. So the first one is X node, the initial electric field along the positive, along the theta direction, so we define as positive. And this side is the X node, opposite to the theta direction. So we can get a solution for this equation. So here, if we further record clearly for the propagation of the electric field, it is the electric field is radiated from source. All right. So we define our source is along this in the Cartesian coordinate system. For example, this is theta direction. This is x. Okay. So this is the source point. It can only propagate along this theta direction, we assume. So we can usually neglect this part, and we can only consider this part here. And for the magnetic field also. So here we just consider the electric field along the only has x component. That means the magnetic field has only a y component, right? So hy theta can be hy node plus also along the theta direction. This one, because it can be expressed as the ex node plus. It has unit, right? It has parameter right here. It's k divided by omega mu. You ready? And I don't want to conduct how this parameter can obtain. I think you can go back to your previous textbook and graduate textbook and get the expressions for this. So we can get the expressions for the electric field and the magnetic field. And for the propagation of H, it should have time variation, right? So the time variation should be included also and it is related to the E, J omega t. All right. Correct. So for the instant or instantaneous electric field, it can be expressed as, so it only propagates along the beta direction, right? It is a transverse electromagnetic field, TM, right? So it can be expressed as data, this part at times the variation, again, the real part of it. All right. So here, and another thing we needed to know or we need to express is this electric field. This electric field, it has, because it is a complex quantity. All right. So firstly, we define it as Ex node bus, right? Because we just consider it along the x direction. And also, it has something, right? Because it also has a phase angle, right? So this phase angle, we define it as this one, initial phase angle. Usually, we can set it to be 0 as the initial figure, and this initial phase angle. But here we just keep it, and so this equation becomes what? Because it has only x component, and real part. This should be a real parameter, right? Real part inside of it is E, and also we have this part. This part again, J omega, and this is minus J k theta. So minus J k theta E J plus E J omega t. So the real part of H can be a cosine function, all right? Cosine k omega t minus k theta plus y plus phase angle. So usually the phase angle, we can set it. Maybe the initial phase angle is 0. Right? There's only 2 terms. So why we want to get this part? Because it represents the propagation of the phase, right? So it's related to phase velocity. So here, if this part is the phase velocity is really defined by phase velocity, right? It's really defined by omega over k, right? And the k, as we previously know, it can be expressed as mu epsilon over epsilon prime for lossless medium, and can be expressed as above. There's omega there, like this one. So this is the phase velocity. Okay, we need to hurry up. So, and it's related to the vacuum, right? So it's related to wavelength can also be obtained. So for this is for material. So if we want to go back to the this part, if the phase velocity in free space, so for it is in free space, that means epsilon prime should be 1, alright, for free space. So the phase velocity can be expressed as 1 over mu equals mu node, right? So phase one equals c, speed of light, in vacuum or in first phase. Should be 3 times 10 to the power 8. And also the intrinsic impedance. This is also important parameter, expressed as mu node over epsilon node, like this, equals 125. So this is a constant, just remember it for our later calculations. So here we just introduced the several parameters for propagation of the electromagnetic waves. Later, I'm going to skip the relationships between the electric and magnetic fields. Just go back to the wave polarization. So for the wave polarization, I think most of you know that it has linear polarization, circular polarized, or the elliptical polarization. All right. So for the linearly polarization, the linear polarization is mostly we used because it's simple, right? Firstly, it is simple, and it has only 2 conditions. Linear polarization. So it only has in phase or out of phase, right? Out of phase. That means it's what? It's locus. Its locus only follows a straight line, and so for the maybe for the circular polarization, it follows a circle, right? So for these things, I would not want to introduce more details about that, because we do not have enough time on that. The only thing is about the elliptical polarization. For the elliptical polarization, we need to clear about elliptical. The ratio or the auxiliary angle between the x component or the y component in the Cartesian coordinate system. So this is the polarization here. So now we wanted to know, we wanted to switch to the lossy medium. Lossy medium, or the loss material here. So when we go back to the propagation constant, gamma square, it equals minus wave number squared, right? So, and previously for the lossless medium, the k square should be a real number, right? Because it's the imaginary part of the dielectric constant can be neglected. But here, for the lossy medium, it cannot be neglected, and be expressed as minus omega square mu epsilon node. Epsilon previously it is prime, right? But now it becomes epsilon. It is complex number. The complex number can be expressed as mu epsilon node, epsilon prime minus j, epsilon double prime, right? The real part and the imaginary part. So if we wanted to change it should be a different form. For example, the propagation constant. The propagation constant gamma can be expressed as also a real part plus an imaginary part. So this is the same definition or the same situation with the dielectric constant. But here, the propagation constant, it has a real part and an imaginary part. So the real part corresponds to who knows? Maybe somebody knows. Some guys know. Alpha is called attenuation constant. Then beta is called phase constant. So, which means if we want to calculate the attenuation of the EM waves when it propagates through the medium, so we need to get the value of alpha, right? Sometimes I think if you really use that value directly when it is defined as something like -meter or dB per meter or per kilometer, something like that one. Alright, we just use the Lambert's law to calculate the attenuation suffered by an EM wave or a channel when it propagates through a material or a medium. And so if we combine both together, we can get the expressions for both parameters. So the attenuation constant can be expressed as minus omega square root mu epsilon naught imaginary part of the epsilon, and the phase constant must be exactly like this. The real part of the dielectric force. This one, measuring part. Okay, and sometimes we have, if we wanted to get, if you obtain the real part and the imaginary part of these materials, when you substitute them into these equations, both equations, we'll get a more complicated equation here. But here I do not want to conduct that. But this is the basic expressions for these both constant parameters, these constants, or these parameters. And here, again, when we come back to the our definition for the material, firstly, we set the material is homogeneous. Right? First, the material is homogeneous, and it is also isotopic materials. So that means if this material is inhomogeneous, for example, you want to conduct the we'll set the snow or the rain as medium, and then the EM wave propagates inside of it because it is not homogeneous, right? So we cannot use both expressions to define the attenuation or the phase variation by that one. And usually, actually, when my master student tried that one and wanted to calculate some complicated situations, and we found that both constant parameters usually fail for the inhomogeneous media, such situations. So this is the expressions for the propagation of the phase of the attenuation variation that. And also we have another one as the what? Previously we said that for the conductive material, alright? So if it has an imaginary part. Is that so? The power are going to be attenuated or absorbed, and it is converted into energy. All right. So that means because if the magnetic wave can be absorbed, that means it can propagate inside this medium, right? So is there, or it is true that any kind of EM waves can penetrate, or is it true that the EM waves can penetrate all kinds of materials? Actually not, right? Especially for the metallic material, it cannot penetrate through it because it has a distance, right? And propagation distance, which we define it as skin depth. Skin depth means the distance of the EM wave which can penetrate inside the material. So the skin depth is defined by these brackets delta S. It is equals 1 over alpha. So it is related to the attenuation constant. And so this is a definition of skin depth, right? And which means for the skin depth, which means what? Which means this is theta, this is the detective electric field with respect to the initial part. So the electric field, the evolution of the electric field. So at the surface it is from 1 to 0, right? Then when it penetrates into this material, its electric field decreases, right? So the skin depth is related to here is 1 over d, right? So this is around 0.37. So when it's reduced from the ratio, it's reduced to be the 0.37 times the initial electric field, then the corresponding depth or distance is defined as the skin depth here. So usually, what we consider as, we hope, for example, if we wanted to put a kind of material for the attenuation of the electromagnetic field, sometimes it want to isolate or totally reflect the EM wave. So we should define the thickness of the material to be at least 3 times the skin depth. So after 3 times the skin depth, its field magnitude reduced to 5% of the initial electric field. So that's why 3 times 0%. For this year, last semester, we took the interview for the entrance examination of the PhD students. So we have a question about the thickness of material which used to isolate the electromagnetic waves. So the thickness of it should be, it cannot be only just 1 of the skin depth, it should be 3 of the skin depth, because it makes the electric field reduced to be 5% of the initial values. So for the lossy medium, we should also classify it to be several kinds, right? So for the lossy medium, usually we have 3 times actually. So the first one is maybe is what? It's a low loss dielectric. Low loss. Right? For the low loss dielectric, that means the real part and the imaginary part of the ratio of the imaginary part and the real part is much, much smaller than 1. So it should be smaller than 10 minus 2. So the low loss medium. And for the if it is larger than, much larger than 1, much larger than 1, it's larger than 100. So that means the imaginary part is much larger than the real part. It can be defined as a good conductor. If varies between both, like then this one is smaller than this one, we can call it a quasi-conductor. Quasi-conductor here. And so for the low loss dielectrics and good conductors, our previous expressions can be simplified, right? So our previous expressions, all these expressions here, is suitable for all these 3 conditions, especially for this one. But if this value and this value, these conditions are satisfied, so that means the previous expressions here, this part can be simplified, right? They can be only maybe a real part. For example, for the good conductor, there is only a imaginary part, all right? It's much larger than the real part, so it can be only becomes prime. Yeah, right. This one. And for the real part, for the low loss media, it only has the real part left, and then both expressions can be simplified. So we have expressions for this one. So for the low loss dielectric, the real part or the attenuation constant, it can be expressed as pi double prime divided by the node times prime, like this one. And I will not conduct the I will not show the conductions for the expressions. So this one is 2 pi lambda node divided by times the square root this part. And we need to take care of it because now the unit of this one is MD over meter. This one is radians over meter. It's unit. Take care of its unit, right? It's different from what we usually used because what we usually use is Lambert's law, Beer's Lambert law. It can be expressed as like this one, right? Right? It's like this one. Because if we want to express it like this one, that means it's in linear region, right? It's in a linear scale. And we really set it to be in the logarithmic scale 10 times this equation, right? So it can be expressed as minus alpha beta times 10 logarithm a minus 1, right? So this one can be expressed as minus minus 4.34. So the calculation of this part is, of course, 4.34 times R theta. So this is converted to be the what? dB per meter. All right. This is for the dB. Previously, this is just for the electric field, but for the power, there is a factor 2. All right. R for the power square. All right. So this is square. Oh, this is 2 times. So this becomes 8.68. So if you read the code, sometimes maybe from others, and you can find that when we get the attenuation constant, and when we calculate the power loss, find there is parameter 8.68. So you should know that it's because it's converted from the linear scale to the logarithmic scale. So it becomes like this one. So theta is the propagation constant of the signal or the channel, and then the propagation distance, right? So maybe meters or maybe kilometers, something like that. Okay, this is for the low loss dielectric constant. For the good conductor, the alpha becomes, because the imaginary part is much larger, so divided by lambda node, and the phase constant becomes also equals alpha and pi over 2 epsilon double prime divided by lambda node. Lambda node means the wavelength in free space, and because the it propagates in a medium with its dielectric constant, or the relative dielectric constant is not equal to 1. So the lambda, the wavelength can be changed, all right? So this is the expressions for the propagation constant, the attenuation constant, and the phase constant for the electromagnetic waves. And just remember that it's just for the homogeneous medium, and if the medium is homogeneous or isotropic, then these equations cannot be used, and we need to find other different materials for that one. Because, for example, if we have maybe several layers of materials, right? The first one is epsilon 1, the second layer is epsilon 2, third layer is epsilon 3, and fourth layer is epsilon 4. So now it cannot be, it will not be homogeneous, right? Even though each layer is homogeneous, but for the whole material or for the whole medium, it cannot be homogeneous. And when we want to calculate this situation, we need to take one layer as an example, and alright, layer by layer, and propagate reflection, transmission, something like that one. And for each layer, we set or we use the basic expressions and then combine them together, and that should be the propagation of the EM waves in multiple layers of the materials. And for certain situations, we should introduce that the density and the next courses. So this is for the expressions for the low loss medium and the good conductor for the calculation. And also we should know the lossless medium. For the lossless medium, we need to know the is Poynting vector and its energy blocks, something like that, and we should also introduce that on Wednesday. Okay, now today our course is done, I think, and see you on Wednesday. Follow Wednesday. Okay, I will share my notes in our IBIT app, and I think you can find it from there. And we have, I think we have one student, one guy is not in the group, not in the app group. It's Dean, and do you know him? Upper Dean. I cannot find that guy from our system, and I just know his name and his number, but I cannot find him. Okay, 你们干嘛不走？再见，拜。
我等不了车，我拿车呢。
他在这边上课。
啊，对，我等。
他上什么课？
没问题。我俩都选了一门电子测量。
对，电子测量是。电子测量是谁上？
林玉杰老师来上。
林玉杰，林玉杰上的电子测量。哎，信息。
他有好几个老师上的。
林玉杰老师做电子测量应该都挺多的。讲的会不会太快？
写上的话能听不太懂，就是说的话，可能有人会听不太懂。